Before we can get into adjusted R-squared, we first need to revisit R-squared. So recall that R-squared is the proportion of variation explained by our model. And I actually prefer to think of it as 1 minus the proportion of variation not explained by our model. So that is, R-squared is 1 minus the variance of our epsilon error, that random noise, divided by the total variation. So that's just the variation of our y. And here we have that written out. So that would be the summation of the model residuals divided by n, divided by the residuals of an intercept model divided by n. And then 1 minus all of that, because we want the proportion of variation explained, of the unexplained variance. So that's what R-squared is, but the issue with this is that in this formulation we're using biased estimates. So we're just dividing by the sample size, where we know that we're actually supposed to divide by the degrees of freedom for our estimates. As you add more parameters to your model, your R-squared is always going to improve. However, when we actually use the adjusted R-squared, or the second formulation where we divide by the degrees of freedom, that won't necessarily be the case, and that makes more intuitive sense in terms of using it as a means to assess performance of your model, right? So that's an issue with R-squared. It's going to be monotonically increasing as you add more parameters when you're looking at a training data set. But adjusted R-squared is going to take into consideration how many moving parts you actually have within your model. So now, looking ahead towards what we need to do within this actual problem, we want to know how to formulate adjusted R-squared in terms of our R-squared. So again, we have what our adjusted R-squared is. So I'm just pulling out these constants. So they're both 1 divided by those quantities, so we just flip the numerator and the denominator because it's a superfraction. And then the next step is to do 1 minus both of those quantities. So 1 minus adjusted R-squared is just 1 minus adjusted R-squared. And then 1 minus all of this mess is going to 1 minus 1 is going to cancel, and then this negative becomes positive. So that's how we get to this second row here. And then once we've done that, we just need to recognize that this fraction is equivalent to 1 minus R-squared. And with that, we now have this nice little formula here to eventually plug in all the values we're going to have to solve to get the adjusted R-squared. And the last thing is just we need to know that degrees of freedom of our model is going to be the number of observations subtract the number of moving parameters. So that's going to be the number of predictor variables you have, and then additionally -1 for the intercept term. First off, just how many observations are we dealing with? So we know that there is 493 degrees of freedom from the problem, and we know that there are 12 predictor variables and an intercept. So using that information, we can then solve for n and get 506. And then it's just plug and chug. So we know that the R-squared is 74%, and we just solve for n and p. Sorry, p was actually given to us, so that's that 12 parameters. And then we plug everything in, we solve for the adjusted R-squared, and we get 73.4%. And scrolling up, we see that falls in the range of C. You should at least be able to know that adjusted R-squared is always going to be less than R-squared. And given that we know R-squared is 0.7406, we know for sure the answer can't be E. And while there is 0.0006 range where it could be D, it's probably not D either. So really you can knock out E and D as options and know that it's only A, B, or C. So worst case scenario, you can guess between those 3 options in an exam setting. But with that, thanks for watching.